We'll have a very brief introduction to the image processing and why we require it, and we'll see the satellite perspective. Main thing is what is image formation and how the representation is done. So we'll talk about image formation and representation first. So what is the simple model of image formation? You need to have a point source or any source of illumination, then you have an object, and then the camera. So the scene is illuminated by the single camera. The scene reflects radiation towards the camera, and this camera senses it via, say, some CCD camera solid state cells. There are two parts to the image formation process. First is the geometry, that is the image plane or the projection of a point in the scene where it will be located. I'll show you how it is done. And the physics of light, because this is an object, some illumination is done, and then this object or this material reflect. So this is the illumination IXY, this is the reflectance RXY. If you combine them, you get the image. This is the brightness of any point. So I stands for illumination, R for reflectance. So let us design a camera. Then you will realize how we come across and how we design a camera, and then we take image and process it. So if I have an object and this is a film, so what is going to go? I can project it from this point to this point, and from this point to this point, and all those in between. So what is the problem? This is also a point again, from this point to this point. Can you imagine the blurring of each and every point? Because these are only 2 points, there will be hundreds of points. We need to be more selective. So the best idea is to put a barrier in between. We'll have a small opening, we call it as an aperture, to block off most of the rays, so this will reduce blurring. So what will happen now? All these will be stopped and this will pass, and we'll get, this is what I was talking about, the image plane. This is the film, this image, this point comes around here, right? Next, again same thing will happen. We'll get only few points here. So we'll have, or we have already studied in our earlier classes, pinhole camera model, the simplest device to form an image of 3D scene on a 2D surface. So what happens here? This is a camera. This is a pinhole camera. You have a small opening here. This is an object. It can be anything. Now, because of this small opening, the image is, or because of this, an inverted image is produced on the image plane. So what is the effect of the aperture size? If you have the size larger, you see, one will go here because it has all the opening. So you'll have the blur, you have some blurriness. But what if you have small aperture? There'll be less blurring, but there'll be a problem. There'll be a problem of diffraction, because you know that if the size is very less, then the light tends to diffract. If you vary the aperture size, say 2 millimeter, you get some images in image like this, and you go down, say 0.35 millimeter, you get somewhat clearer image. But what happens if you start or you continue decreasing the aperture size? The problem would be like this. There will be diffraction, there will be scattering in many directions. So what is the solution? Solution is the refraction. Solution is refraction, and you know by now, and you know earlier physics, that bending of wave, or because of the change of the speed from one medium to another medium, this is the refraction. We are aware that we can not have that very small opening, that is the pinhole camera, but we can have something different here. We can put a lens here. Now when we have lens, now the line which is passing through the center will come here, and any line which come here will be diffracted, or sorry, the refracted, not diffracted, but refraction. So the principle of refraction on this lens, because of the refractive index difference between the lens and the outside, you'll get an image. This is what we wanted. So you'll have an image, and let's improve the image quality. We lead to a sharper image like this. So this was good. Okay, this was very fine. You have a very small opening, but this is very fine. You have an image which is quite nice with this use of lens. Okay, now let's just discuss in brief about the thin lens. You can have a thin lens, you can have a large lens, you can have a broad lens, you can have concave lens, you can have a convex lens. There are plenty of lenses which are available. So light rays pass through the center, they are not deviated. Light rays which pass through a point far away from the center, they are deviated more. So you have various focal lengths and U's and V's, the distance between the lens and the film and the point where it converges. So there is a distance from here to here which is called as a focus. This is the focal point where everything focuses. And if you have a thin lens, you can change the lens depending upon what exactly you want or where the film you are going to place. So there is a simple science. You use this similar triangles. These are the similar triangles, and these similar triangles leads to a very fine formula we are all aware of. We have done plenty of questions on this. 1 by u plus 1 by v is equal to 1 by f. V and u are the distances like this, right? This is f. So now this is a thin lens equation. You can have some blurriness, circle of confusion, all those things will come, but this idea is very good. So that is why we use lens in the cameras. But there is another cameras which is the digital camera. So there are different type of cameras. We can have optical camera, we can have a digital camera, and all these uses, of course, the lens. Maybe the digital camera replaces the film, which is the film. We are not talking about the lens. Lens will always be there. We are talking about the sensor array, or we are talking about the film. So each cell in the array is light sensitive diode that converts photon to electrons. And there are two common types: CCD, charge coupled devices, and then complementary metal oxide semiconductors, right? So now we come to the digital camera. This is the illumination. We go back again to where we started. This is the basic idea of how the image is made. This is the illumination source. This is a scene element. And when this light is taken up by the imaging system, and you have an array, this image which is taken is because you have an array. So you will have one array or one pixel in particular array. So what happens here in CCD camera? CCD moves this photo generated charge from pixel to pixel and convert it into voltage at an output node. So you need to have an ADC, analog to digital convert, that turns each pixel into a digital value. What about the CMOS? And CMOS is this converts to voltage inside each element. So it uses several transistors to each pixel to amplify and move the charge using more traditional wires. So the CMOS signal is digital, so it needs no ADC. CMOS directly you will get the digital signal. CCD you need to have ADC. So image digitization, as we just saw, this point comes here, this point comes here, and this actual image will be seen like this. So you have two processes here: sampling and quantization. Every signal we take certain samples. This is sampling. More the sampling, good is your image. Quantization means any point or all the points are being mapped to a single point. How? See, this is a light for a particular image. You get a single signal like this. We take different samples here. Okay. Now these samples, these are mapped to certain points, and these are the quantized points. So you can get, say, you have 8-bit image, so you'll get 0 to 255 values. You have, say, 2-bit image, you will get 0 to 4 values only in the array or the digital space of the matrix. So what is an image? This is an image. These values vary from 0 to 255. 0 means black, white means 255, and gray, of course, is in between 0 and 255. So what is an image? As we come along, again, it is a two-dimensional intensity function like this. So we'll talk about this again. A digital image is discrete. That means it is sampled and quantized version of this function. How far you can sample, the more sampling you do, the more or the closer samples you take, you get better image. Otherwise you'll get image like this. And when you quantize, See the quantization level. If the quantization level is high, 8 bit per pixel or say 10 bit per pixel, the image will be like this. Otherwise, you'll get like this, right? So this is how you can vary image quantization and sampling. It depends on you. These are common image file formats: GIF, PNG, JPEG, TIFF, PGM, FITS. There are many more. I've just stated few of them. So the image processing, the definition is you want to represent an object. The image is considered to be a function, as we just saw, of two variables, a, x, y, where a is our amplitude or brightness, digital number, digital value. All these are similar and they are on a real coordinate position. I'll show you how. So why we need processing? This is image and processing. Processing means operation to produce something. It depends on your desired output. So image processing is nothing but the collection of various algorithms, various mathematics which are involved to manipulate the image for better usage. For that, if you have desired output of image processing, of course you'll have an image. If you are doing image analysis, you want certain measurements. If you're doing image understanding, you want some high-level descriptions. But before we go ahead, let me tell you that normal image, satellite image, every image are similar. Some differences are there, but we deal with them equally. If your image is there, you have taken it from digital camera, or I have an image which is taken from satellite, I'm going to apply most of the filters, most of the operations in a similar way. So in image acquisition system, you have an object, sensor senses this object, you have an analog to digital converter which converts it into a digital image. And there are various factors you have to understand. Electromagnetic spectrum, dynamic range of the sensor, reflectivity of the object, the resolution. We'll talk about this. So you can have a single band, color, multi-band, multispectral, hyperspectral images. There are various variety. So now we are aware that our image is formed like this. So you have a continuous color discrete locations. Now you have a discrete real valid image. If you talk about a satellite, so it depends on what is the IFOV, that is the instantaneous field of view. This area, there are various mathematics involved, various angles and geometries are involved, but you get a digital image only. So this is the image which you get. Digital image, this is one band. You can have multiple band. Multiple band means various you are aware of the electromagnetic spectrum, say 0.4 to 0.7 is visible. You take image from 0.42 to 0.46. I say I take from 0.56 to 0.68. So this is the one band, this is another band. So there are variety of bands which various satellite uses. So one band is like this. So you have a row and a column, and at each junction, or you can say at every point, you have a brightness value which is given by the row and column and the band. So if I say 442, you can have a band or similar 44, this 24 one of this one here, and like this. So this is how it vary. We have already discussed this. Resolution, there are various resolutions: spectral, radiometric, and spatial and temporal resolution. Temporal resolution is specific to the satellites, but other resolution are for every images, because spectral resolution means in which frequency or electromagnetic spectrum band you have taken. Say I have taken from 0.4 to 0.5. I will come up with other one comes up with an idea 0.42 to 0.646. I say I've taken image from 0.421 to 0.422. So I have a better spectral resolution. What about radiometric resolution? When I am trying to quantize it, then I say I have quantized it to 8-bit. So you will have a value in that digital image. The digital values will be from 0 to 255. Somebody comes up to me, I have an Iconos image. It is quantized up to 11-bit. So radiometric resolution, I can vary up to 2047. This is radiometric resolution. So I have a better grayscale variation. What about the spatial resolution? Spatial resolution, how far? Because I have an image. Somebody comes up to me and he says, this is my image. I say, no, I have this image. I have divided it again. So I have many more pixels to represent the same image. I have more data. So that is spatial resolution. So I can pinpoint the various points on the ground or the details in the image. Temporal resolution means, I'll just come to that. Spectral resolution, let us see. These are the spectral resolution, various bands images are taken. And then the radiometric means how many bits you take to represent the image. Then the temporal resolution. Now temporal resolution means if we are talking about satellite, the satellite comes over this area here. Satellite is above and this is the area beneath, say the nadir point. Now this satellite comes and revolves again, and this comes here. Now it can tilt the camera or the imaging device and it can take the image, but no, we are not interested in this. We are interested that when this satellite is going to come exactly over this path, that is the temporal resolution. So why do we need pre-processing of remotely sensed image or any image? Because images may have flaws or deficiency. So there are various pre-processing operations that we do depending upon the situation, and there are various pre-processing techniques available. You can have feature extraction, say you have dimensionality, say hyperspectral image or ultraspectral image. Say hyperspectral has 200 bands. How are you going to deal with it? Your electron gun or your gun in the display device only have RGB, so you can only deal with 3 bands at a time or 3 images at a time. I must say 24 bit per pixel, 8 bit, 8 bit, 8 bit. So now you need to select, so you can do the dimensional reduction. You can use the radiometric correction, geometric correction, atmospheric correction. So why do you need image enhancement? For our visual interpretation. I want good understanding. I want image to be clean, good, beautiful. Enhancement, you can have a point in enhancement. You can have a local operations. You can have spectral enhancement. So radiometric enhancement means you are modifying the brightness value of the image. Each value you are modifying. Spatial enhancement means an area. All these area means spatial enhancement of surrounding pixels, with local operations you want. And spectral enhancement means you are doing or enhancing image in the multi-band basis, means RGB-A or near infrared RGB, like this. So image, we come to image reduction, magnification. This is all what you do normally when you have an image. You magnify it, you reduce it just to have a proper visual interpretation. So image reduction can be done like this. This is your original image. You can just crop off or leave all these pixels, just show these pixels, or you can take just these pixels and show like this. So we are just taking off this line, this line, this line, this alternate row and column we are taking off, and this is image reduction. But if I want zooming or image magnification, what we are going to do, we are replacing this again and again, row wise also and column wise also, right? 2 to 4, then 2 to 4, 2 to 4, so it will be enhanced. Now radiometric enhancement means the modification of brightness value of each pixel, that is the point operation. So we have various science involved here. You can do the brightness and contrast and adjustment, histogram equalization, histogram matching, color correction, gamma correction. So histogram is nothing but the frequency distribution of the pixels in the image. So this histogram is nothing but the number of pixels in that image which are having certain value. This is the histogram. So histogram, the representation is very important as far as image processing is concerned. This is just the representation of the frequency, number of times a pixel is appearing in an image. Contrast means the difference between average gray level of an object, that of the surrounding. You can say difference in illumination or gray level values of an image, or you can say how vivid or washed out an image would appear, or you can also say ratio of maximum intensity to minimum intensity. So contrast will be maximum gray value by minimum gray value. So why you need contrast stretch? See this image. Are you able to see something? Let me stretch this band too. This is the contrast stretch. This is how the image will appear. So the reason of low contrast can be the scene itself has low contrast ratio. The sensitivity of the detectors may be a problem, or of course the atmospheric scattering if you are taking it from satellite. So you have a low contrast image and you have a histogram like this. I want to enhance the contrast using this histogram. So how you see how I just by contrast stretching I had the image which is viewed something different. So contrast enhancement type can be linear contrast stretch. In this, the input and output data values follow a linear relationship: min-max stretch, percentage stretch, standard deviation stretch, piecewise linear stretch. Or you can have a non-linear contrast stretch. The input and output data values do not follow a linear relationship. You'll see that in the diagram coming. There is logarithmic, inverse log, exponential, square, or square root. So linear contrast stretch is quite easy. It can be you have a Gaussian or non-Gaussian curve. So what you do, this is the minimum, this is maximum, this is the whole range. We are not utilizing this range. Why not to map this minimum to here, this maximum to here, and likewise all others can be mapped. So this is the enhancement of the image. Or you can use a lookup table. Say for 0 you take, for 10 you take 0 or map it to 0. You map 52 to 55. So only the variation from 10 to 50 means you have a whole lot of dynamic range. You are using this. So I'm just stretching it to the limits. You can also have standard deviation linear stretch. What happens? This is the standard deviation. You have sigma here. So sigma, this is 1 sigma, this is 1 sigma, this is 2 sigma, this is 3 sigma. So 1 sigma, 2 sigma, 3 sigma. In this sigma, what we have done, the values which are coming after 1 sigma, you stretch them. The value which are coming after 2 sigma, you stretch them. So this is called the standard deviation linear stretch. You can also have a logarithmic contrast stretch. In this, what you do, you take the data, you take the log out of it, and then you try to stretch it. So for that, the best thing is the stretch has greatest impact on the brightness value, and the darker part will, you'll have a bright part, more bright, darker may become more darker. So these are the non-linear contrast enhancement. These are the various types, and I've just showed you. Let me show you the diagram also of the non-linear stretch. You can have log, nth root, nth power, identity, inverse log. All these are there with you. Now we come to the histogram equalization. This is very important because histogram equalization means this original image is redistributed to produce a uniform population density. If certain population is limited, you might not to redistribute them. So you have, or you can obtain it by grouping certain adjacent gray values. So the number of gray values in the enhanced image is less than the number of gray values in the original image. So contrast is increased at the most populated range of brightness values of the histogram. That is, we call them as the peaks. So it automatically reduces the contrast in very light and dark parts of the image associated with the tails of the normally distributed histogram. Histogram is very important. See histogram, and you have this is only, population density is very low. Why not to redistribute it? And see, we have redistributed, and this is our satellite image. This is how histogram equalization gives you. And you can also have histogram matching. You have a beautiful image, you know the histogram, and you have a histogram of another image, you want to match it with it, so that this becomes like this. This is histogram matching. Spatial frequency, the number of changes in the brightness value per unit distance for any particular part of the image. Image becomes composed of high frequency and low frequency details. High frequency or near frequency means the low frequency means few or very less changes in brightness values over a given area. High frequency details means brightness values change dramatically. So this is the zero spatial frequency, flat image, no change. This is a gradual change, and here highest spatial frequency. So there are filter types. Low pass filters, it will only allow the low frequencies to pass. High pass filter, it will only allow to pass the high frequency. So low pass filter, they block high frequency detail, have a smoothing effect on the image. They remove the noise, basically salt and pepper kind of noise, and blurring of image, especially at edges. What about high pass filters? This preserves high frequency and removes slowly varying components. It emphasizes fine details and used for image detection and enhancement. The edges, the locations where transition occurs. So edge detection means if you can find the edge, that is the transition, which is very abrupt, and this can be done like this. So you have various options for that. You have to do the smoothing, then the enhancement, then the thresholding, and the localization. You can use the derivatives, that is the first derivative and the second derivative. You can find from first derivative and the second derivative the exact zero crossing where actually the edge is there, or you can use the gradient. Gradient is very del over del x you can take, del over del y you can take, and just you can take the magnitude of squaring them and adding them, and direction also. So you can get the directions also, the magnitude and direction. For example, this is just an example because you have Prevet, the Sobels, and various operators there. I just want to introduce one of them. This is mx, this is my. So what you're doing, you are enforcing this on this. So -1 into 38 plus 0 into 66, like this, fx. In x direction, then you take the y direction. So you have fx here, you have fy there, then you get delta f by squaring them and taking root. This is your magnitude. Now theta you can get in easily by tan inverse of 16 by 18 here. And now this is the way in image, if you are using the gradient, this is di by dy. In the y direction, this is di by dx. Square them and add them, you see how you can get the edges clearly. So this is the example of edge detection, a simple example, thresholded image, detected image. And now density slicing. Density slicing, in image processing and satellite image processing, mostly in the classification activity, we would require this. And there are various activities also. What happens that I have a range of pixels, say 76 to 84, I want to make it green. I need to say that, okay, I have realized that some is water, some is land, some is say marshy land or sandy area. So I can just give colors to them. So this is density slicing. Pixelization means, say somebody is standing, these have nothing to do with him. So I need to pixelize. So this is how we pixelize. Original image, we go down, means, we make the resolution coarse, and then we can just do the pixelization. Image compositing is also there. We can combine the part of separate image to form a new image. This is quite difficult. There are certain aspects which we need to see and how it is done. Say he is at home, now he need a better shot. This area. So this area. So we can have a better shot like this. This shot demands a monogram. You need to have a monogram here. So we can have a monogram also. And now this is how an introduction of image processing. This only gives you a brief idea that how we start with image formation, and then you can apply various image processing. This is just a glimpse. There are various image processing algorithms and techniques available. I hope you can get a few of it. Thank you so much. Take care of yourself.